Hello everyone, in this video we'll be looking at section 9.9, which is representation of functions by a power series. So in the previous section we were given some power series and we knew that that power series was representative of a function and we had to find its radius of convergence. So now what we're going to do is being given a function and have to find its power series. All right, so we're like going the other way around. Okay, so let's start with subsection 1 here, which is geometric power series. So in this section, we will study several techniques for finding a power series that represents a function. So consider the function f of x equals 1 minus x. The form of f closely resembles that of the sum of a geometric series, right? This 1 over 1 minus x is very similar to this a over 1 minus r. And we know that this geometric series converges if the absolute value is less than 1, right? So in other words, if a equals 1 and r equals x, then we can write this 1 over 1 minus x as this power series, right? In other words, we're saying, hey, we've got this, now let's write it like this, right? So we know that 1 over 1 minus x is equal to the sum from n equals to 0, and I'm just going to go ahead and write a times r to the n, but remember in this case, what is our a? Our a is 1, so I can rewrite this as 1, and then what is r? R is x, so x to the n, so in other words, this looks like x to the n, which looks like 1 plus x squared plus x cubed, and so on. Right? So 1 over 1 minus x can be represented as this power series when this converges, or this is a good representation because it converges when, well, in general, the absolute value of r is less than 1, right? But what is r in this case? R is x, right? So in other words, when x is less than 1, right? So what does that mean? That means our radius of convergence is r equals to 1. And since we're centered at x equals to 0, why are we centered at x equals to 0? Because it's not x minus something. And so if this is negative 1 and 1, we know that my radius of convergence being 1 means all these values are fine. Right? So in other words, this series, I'm able to rewrite 1 over 1 minus x as the series 1 plus x squared plus x cubed and so on, as long as x is between negative 1 and 1. Outside of that interval, this is no longer a good representation of 1 over 1 minus x. So again, one thing to notice here, this is on the open interval from negative 1 to 1. What happens when x equals to 1, right? Not included in this interval because of the open part, but what happens when x is equal to 1? Well, when x is equal to 1, f of x, which is 1 over 1 minus x, is not defined, right? So to represent f on another interval, we have to develop a different series. So to obtain a power series centered at x equals to negative 1, what do we need to do? We rewrite our series 1 over 1, or our function 1 over 1 minus x, and make it look like something over 1 minus, and since we're centered at x equals negative 1, it'd be x minus negative 1, so in other words, x plus 1. And this would give us, and then we use this to rewrite it as a and then x plus 1 to the n, right? So that's kind of our goal, is to rewrite our function so it looks like that, so that I can rewrite it as a power series, right? So now this requires a little bit of algebra manipulation. So 1 over 1 minus x. So I need to get x plus 1 in the denominator, right, over here. So I have 1 minus x, right, that's what I'm starting out with, and now I'm going to add and subtract things to try to get this. So say, for instance, I tried to add plus 1 here, and then if I added 1, then to balance out, you have to do minus 1 there, right, and I'll just leave the 1 in the numerator alone. If I did this, notice what happens is right here, I end up getting, if I tried to, remember I want x, 1 minus the quantity x minus 1. If I factored out a negative, I'd be left with x minus 1, or I'm sorry, minus the quantity x minus 1, which is not what I want, right? I want minus x plus 1. So in other words, what I have to do here, again, I have 1 minus x, and I'm going to do the same thing to both sides, so that way it's a balanced equation. I'm going to subtract 1 here, and if I subtract 1, that means that I need to add 1 there. So I add and subtract the same thing to both sides, so that means it's a legal move. Now, if I factor out a negative here, I'm left with these two add up to be 2, and then minus, if I factor out a negative, I get x plus 1, which is what I want, right? Remember, I want something over 1 minus x plus 1. So I'm almost there. But now the issue is this pesky 2, right? That needs to be a 1. So what can I do? I can factor out a 2 out of the denominator, right? If I factor out a 2 out of the denominator, I'm left with 1 minus, and then it's going to have to be a bigger parenthesis, because what do I multiply x plus 1 by, or I'm sorry, what do I multiply here? What am I trying to say? What do I need to multiply 2 times x plus 1 over 2 in order to get x plus 1 by itself, right? To kind of go backwards, right? Because then if I multiply this, if I distribute, I'm back up into the previous step, right? Okay, so now I have almost what I want, right? I have a 1 minus something in the denominator. So what am I going to do here? Every time I have something in the denominator, remember, I can just factor it out like a constant, right? So I can rewrite this as 1/2 times 1 over 1 minus, and then now instead of writing x plus 1 in parentheses over 2, I can rewrite this as x plus 1 over 2 all in parentheses, right? Again, that's just fancy footwork of the parentheses there. Okay, so now I'm almost what I want, but I don't want this 1/2 out front. So I'm going to take this 1/2 and pull it up into the numerator, right? Because that's fair game because it's a constant. So I end up with 1/2 over 1 minus x plus 1 over 2. Now this is exactly in the form that I want, right? So in this section, we're going to be doing a lot of fancy footwork here with algebra. So make sure you follow what I just did in all of those steps, right? A lot of times we're going to have to be adding two things so that we keep the equation balanced, or adding and subtracting the same thing. A lot of times we're going to be factoring things out, which is what we did right here. A lot of times we'll be playing with pulling coefficients into the numerator or from the denominator into the numerator. So we need to make sure that we know how to do all of those tricks, right? And we'll practice those in the examples. So what did we figure out here? Well, whatever's in the numerator, remember, is my a. So a is equal to 1/2, and r is equal to whatever I'm subtracting here. So I get x plus 1 over 2. Okay, so what does that mean? X plus 1, so we end up getting that by the geometric series formula, right? What does this tell us? It says that every time I have something of this form, right, I have 1/2 over 1 minus x plus 1 over 2, I can rewrite it as this sum, right? So I can rewrite my guy 1 over the original guy, which was 1 over 1 minus x, as 1 over, or I'm sorry, as 1/2 over 1 over 1 minus x plus 1 over 2. And then now I can use the geometric series formula, which starts at n equals 0. And I can plug in A in this case is 1/2. And R is x plus 1 over 2 to the nth. Right? This is that the geometric series formula. Oops, A times R to the n. Right? So this is another representation of it. And when is this? It's very important. This converges when what? My R, my absolute value of R, which is the absolute value of x plus 1 over 2, is less than 1, right? Because that's what we have here in green. But that we can rewrite. Remember, we can play that trick where we take the absolute value of 2 in the denominator and multiply it, and end up getting that x plus 1 in the absolute value is less than 2. So what does that mean? That means I have a radius of convergence which is r equals to 2. And if I think about what this looks on the number line, remember, where was this one centered? This one was centered at x equals -1. So I add 2, I get to +1. I subtract 2, I get to -3. So on this interval, I can write 1 over 1 minus x as this infinite sum here, right here. And again, on this interval from -1 to 1, I had to represent it this way, right? So I'm getting different representations of my my function as a series depending on the different intervals that I have, right? Okay, so what we're going to do, that was a very specific example. So now let's look at different examples where we try to find the power series of a given function centered at a certain point. And so basically the idea here is exactly what we just did in that last kind of example, illustrating the function 1 over 1 minus x, right? So our goal here, just like before, we rewrite 4 over x plus 2 as we want to rewrite f of x equals 4 over x plus 2 as a over 1 minus r, and then we use our formula to write it as the series that looks like this, right? So that's the game plan. Go from here to here, and then from there to there, right, with known formulas. Okay, so I take 4 over x plus 2. So first thing I like to do is just reorganize the denominator so that my x is over on in the place on the right, right? So I need it to be 1 minus something, right? So what am I going to do first here? I am going to factor out a 2, right? So here, if I factor out a 2 from the denominator, why am I doing this? To get rid of that 2 there, right? Because I need it to be a 1. So I factor out a 2 of the denominator, I'm left with 1 plus, and if I factored out a 2 from x, I need to multiply it by x over 2 to get x back, right? Now what happens, this 2 cancels out with this 4, I'm left with a 2 in the numerator, so I get 2 over 1 plus x over 2. But once again, that's not exactly what I want because I want a minus sign, right? So in order to get a minus sign, I just kind of, it seems like cheating, but I just factor out a negative, right? So I get 1, and now I subtract, and if I subtract there, I need to write minus x over 2. And then I get the 2 in the numerator, right? So I did all this rewriting to see that my numerator is 2, and then my radius is minus x over 2. Right? And that's something that we have to do a lot. This step right here, where we factor out a negative, so that way we make sure to get our minus sign in the denominator. We do that a lot. Right? So now what can I do? I can use my formula for a geometric series. All right, I said, okay, I took my original function as 4 over x plus 2, and I rewrote that as 2 over 1 minus x over 2. And then, remember, I can rewrite this as a geometric series, a times r to the n, by the geometric series formula. But what is our a? Our a is 2, and our r is minus x over 2 to the n. And now, rewriting this, minus x over 2 is the same as negative 1 times x over 2 all to the n. And now rules of exponents say I can distribute that n to both terms. So I rewrite this as n equals 0, 2 times negative 1 to the n times x over 2 to the n. So that is my geometric series for this function f of x equals 4 over x plus 2. But we need to talk about its radius of convergence, right? Remember, when does this converge? Converges when whatever my radius is less than 1, right? What is my radius in this case? My radius is negative x over 2 is less than 1. Right? But the negative is redundant, and then I can multiply by 2, so I end up getting x is less than 2. Right? So my radius of convergence is r equals to 2. And then just for fun, what is my interval of convergence? Well, where am I centered at? I'm centered at x equals to 0. And I have a radius of 2, so this is 2, this is negative 2. So this is what my interval looks like, negative 2 to 2. We just don't know what happens on the endpoints. In this case, actually, the endpoints don't converge. Okay, so let's look at another example here. Find a power series for f of x equals 1 over x centered at 1 and state its radius of convergence. One thing I should note, remember this, because I have my final answer has just x by itself, we know that it's centered at x equals to 0, just like the problem asked us to have it. Typically when you're rewriting these, it will kind of lead you to centering it at the place that they're asking for. But in this case, we should just make note of that in fact we did center it at the right spot. If we somehow got a different value of x minus something or x plus something there, we know we had to do some different algebra. Right? So we want a power series for this guy. So what do we want to do? Our goal here is to rewrite f of x equals 1 over x as a over 1 minus r, and then from there we'll be able to write that as a geometric series, right? So I take 1 over x, and now I'm going to rewrite this. I need something minus x in the denominator. Right? So what I'm going to do is add and subtract the same thing to the denominator and add and subtract the same thing to the denominator. Right? So I have x here, and remember that I want to have this centered at x equals to 1. Right? So in other words, what I want right here is x minus 1. Right? Because if I have an x minus 1 there, then I know that I'm centered at x equals to 1. Right? So if I try to put, let's just say plus 1 here and minus 1 here, then I don't immediately see how I can get minus x minus 1 Actually, that's exactly what I want. Right? Nope, so side note. I don't get what I want because then I have a -1 there that I would have to factor out. Right? So that's not what I want. What I want to do is I do 1 over x, and then what I'm going to do is I'm going to sorry, I'm struggling with this in my head. Yeah, okay. So this is what I want to do. I want to add 1 to the numerator and add 1 into the denominator. So now what I can do is I will factor out a negative. So when I do that, I end up getting 1 minus x plus 1. Right? So again, this seems a little bit awkward because the minus with the x there, and I was looking for x minus 1, but this will work for us. Right? Okay, so what does that mean? That means that my a is equal to 1 and my r is equal to -x plus 1. Which I could rewrite as minus x minus 1, which is what I want, right? Because now I'm centered at 1. Okay, so now I can say this, I can write, okay, 1 over x we rewrote as 1 over 1 minus x plus 1. And now we can use our geometric series formula to rewrite this. What's our a in this case? Our a is 1. Our r is negative x minus 1 quantity, and then to the nth power. So that 1 here is redundant, but I can distribute this n to both terms. So I end up getting -1 to the n, x minus 1 to the n. And that is my series for 1 over x. But now, remember, we have to talk about when it converges to that, right? 1 over x is not always equal to that. It just equals to this sum during a certain interval. So this converges when the absolute value of r is less than 1. In this case, what's my r? My r is negative x minus 1 is less than r, right? But that absolute value takes care of that negative sign. So I get when the absolute value of x minus 1 is less than 1. And again, we're happy about all of this because remember this right here, this x minus 1 there means it's centered at x equals to +1, right? So I think I wrote this wrong. I want x minus 1 to be there, which we ended up getting. And so now what does that mean about my radius of convergence? My radius of convergence is r equals to 1. And just for fun, we're actually going to need it in another problem. Remember, where are we centered at? We're centered at 1, and we have a radius of 1. So I go to 2 and I go to 0. So this is my interval. So my interval of convergence is 0 to 2, not including either value. So we didn't do the work to show that for sure it's an open interval, but for the sake of the problem we'll do later, it's actually for sure an open interval there. Oops. All right, and we'll go ahead and end this video here, and we'll pick up with subsection 2 in the next video.